Hello and welcome to the part B of module 2, where we are going to discuss about logistic regression, or we can say classification. In this lecture, first we introduce the classification, then we are going to define the logistic function and the decision boundary for this classification task. Then we slowly learn what do we mean by hypothesis function and how to train a classifier. Then we extend our concept of binary classification to the multi-class classification. Okay, in this logistic regression, which is better known as classification, we have observed that the output is discrete valued. What does this mean? If you see this example, then in this example there is a group of apples and a group of not apples. So what will be the output of this system based on this separator given an instant which is either apple or not apple? And so its output ranges from 0 to 1. 0 means non-apple, 1 means apple, and so on. So what is the purpose of this classification? So this is the training samples are given here. This is apples and it is saying, look, these are apples and look, these are not apples. So basic idea of the classification problem is that to find out this separator. So in this separator, here in this example, right hand side, you can say that is apples and left hand side is not apples. So when a new instance is being given, we don't know what is this, so that it is in right hand side, so it can say, oh look, this is an apple. That is the performance, or that is the intended output of this. So when a new sample is coming, so that this classification by virtue of this separator, we can say this is apple or not apple. In this case it is apple. So in logistic regression, what we'll see that given a instance, we say that it is either 0 or 1 or plus 1 or minus 1, that in which side of the separator and is apple or not apple, and with some probability that we can say the what probability this instance is apple. Okay. So now how we can do this? For doing this, in classification, we put a sigmoidal nonlinearity over the linear regression hypothesis function. As we know, our linear regression hypothesis function is this HNR for regression phi 0 plus phi 1x. So what we wrap this function with a sigmoidal nonlinearity. Okay, sometimes it's called logistic function. And how it's look like? It is L of z is equal to 1 by 1 plus e to the power minus c. So this is the logistic function. Okay. Now what is this g? This g is basically our linear regression function. So ultimately, if we put this is the logistic function of the classification, that is h phi classifier x is 1 by 1 plus e to the power minus z. So z is what? Z is our phi 0 plus phi 1x. So e to the power minus phi 0 plus phi 1x. Now middle we can say 1 by 1 plus e to the power theta transpose x. But this theta transpose x is this. So this is the sigmoidal nonlinearity. So what it look like? Graphically it is look like. Now if this z is greater than 0.5, it is slowly converts to 1, and if it is a less than 0.5, it's going to 0. Okay, so this is we put over the linear regression function to get the hypothesis function of the logistic regression function. Now let us see a bit mathematically what does this mean. As we understand, in our logistic regression, the hypothesis function does look like this: 1 by 1 plus e to the power minus theta transpose x. Now, what it basically wants, as we understand, if it is a linear regression function, so this line. Now we are putting this curve, and our classification rule is defined that if this thing, this hypothesis function is greater than 0.5, is greater than 0.5, then we can say it is a green circle. Now this is our separator. So if it is a greater than 0.5, it is a green circle. If it is a less than 0.5, it is a red circle. Now this, between this green circle and red circle, this separator is called decision boundary here. What does this mean? That this hypothesis function is greater than 0.5. That means this phi transpose x, this is greater than 0, because you see here this is 0, then only it is going up 0.5. If it is less than 0, it is become is less than 0, that it is less than 0.5. So when we are going to predict y, that in red circle, if this hypothesis function less than 0.5, and that essentially means this phi transpose x less than 0. Okay, so this is the basic definition or basic understanding of the logistic regression. Now what actually it will give, that if we say, okay, our hypothesis function h phi x is 0.6 on input x, and it is a y in a green circle, that means that there is a 60% chance this x data belongs to the green circle. So that is the output of this classification, and we change this logistic function in this way, and this is the mathematical understanding, and this is the visual understanding. Now how to find this separator? So this separator now we call decision boundary. Now as understand that this decision boundary is very essential in classification. Actually, we want to find this decision boundary given these training examples. Here you can see very simple problem, because apples and non-apples given such a way that is linearly separable. So we put a straight line very easily by just grouped them out. Okay, so now take an example to understand how we get this line. Now let this phi transpose x is phi 0 plus phi 1 x 1 phi 2 x 2, where this phi transpose is basically minus k 1 and 1. So these values are 1, k minus k, this is 1 and 1. So if we have to predict y, because y is equal to apple, that what does this mean? We have to predict this. That means we have to say this hypothesis function greater than 0.5, as you see here, is greater than 0.5, or you can see here this greater than 0.5. Okay, now if we say that this h phi cx is greater than 0.5, that essentially means this phi transpose x greater than or equal to 0, as we discussed in the last slide. What does this mean? Here it is minus k plus 1 1, so minus k plus x1 plus x2, we put it here, and this, that means essentially x1 plus x2 greater than or equal to k. When we have to predict y is equal to non-apple, so it is the reverse case, then we have to say that this hypothesis function should be less than 0.5, as we see here is 0.5, so it is red. Now it's a non-apple here. Okay, so phi, suppose x is less than 0, what does this mean? This thing minus k plus x1 x2 less than is equal to 0, but essentially mean x1 x2 is equal to less than k. So this is one equation. But if we say what is the in between, so if x1 plus x2 is equal to k, that is the equation of our decision boundary. So this discriminating line is called decision boundary, and from this example we can understand this is the equation of this discriminator or decision boundary. But one thing is very important to understand here, that this decision boundary is depends on hypothesis function, not on the data set. Maybe just for example, this particular example, these data are linearly separable. It may be the case always that it is not that. It's not always linearly separable. So even if we have this straight line, it is our choice that we have to put whatever is this case. We tolerate some inaccuracy, but we go for the near hypothesis function. So it depends on the nature of the hypothesis function, our decision. Okay. Now the question comes, how accurately or how precisely we can find the decision boundary to separating out two pairs or multiple pairs of data. Maybe in our previous example, we have said there is a binary classification. So there is a set of apples and set of not apples. And the question is that how we can get this decision boundary that clearly separate these two set of data. Now, to answer this question, what we have to first understand, what are the setup of our problem. This is a paired, this is x1 is a data instant and y1 is level. So this is a paired data. And what is k? K is the total number of training examples. What our hypothesis function? That means what is our decision boundary? That is phi c x, that is 1 by 1 plus e to the power minus zeta transpose x. That is basically we put a sigmoidal nonlinearity over this transpose x. And since there is a k variate our input instance, so this h is phi 0 plus phi 1 x1 plus phi 2 and so on phi k x, which is basically in matrix format is phi is put x bar. As you also seen that this phi is this matrix, this x equal to this matrix is k plus 1 dimensional, is also k plus 1 dimensional, and this is the equation. Now we have to find out that phi t such that we can have a very precise decision boundary. So that is the problem formulation. So the loss function of linear regression is j of phi is equal to 1 by m, sum it up over I2 to m half h phi xi minus y square. So it's basically the square error, that is sum it up over 1 to m is number of samples and average it out 1 by 2. And that is the univariate loss function. Now what we'll do, we rewrite this function, that this part we write as a loss of h phi xi yi. Okay. So this loss function becomes this, that j of phi 1 by m sum it over 1 to m loss of h phi xi yi. Now for our logistic regression, this h phi xi is a sigmoidal over this phi transpose x. So 1 by 1 plus e to the power minus phi transpose x. Now you see, in the linear regression, if we plot this function, it was a convex, as you have seen earlier. But if we plot this function, is basically this logistic regression function, then this error surface is non-convex. And what is the problem with non-convex? The local optima or local minima is not similar to the optima. So using gradient descent, we cannot reach here easily. So that is the major problem of this logistic regression loss function. So what we have to do, we have to change this loss function in such a way that we can get this convex function. So to get rid of this problem, we define the loss function of the logistic regression in a different way. So what we are going to do, that if y is equal to 1, that means that our target is basically 1. So our loss is defined is minus log of h by x. And if it is 0, that we supposed to, our hypothesis function will produce 0, should produce 0. Our loss is h phi xi yi. Loss of this is minus log of 1 minus h phi x. Now we have to try to understand how this newly proposed loss function going to help our this logistic regression formula. Now let's try to understand if y is equal to 1. Okay, so what we required or supposed to do that this h phi x, our hypothesis also predict 1. If we can predict 1, we say that or very close to 1, then we can say our classifier is work well or work fine, and the loss is very less or very close to 0, because that is our intent state output and our classifier is working as per our intention. But if y is equal to 1, basically the target, but our classifier is basically 0 or very close to the 0, it means our classifier doing wrongly or poorly. Then we have to penalize this classifier and the corresponding loss is very high or close to 20. So this thing we have to impose. Okay. Similarly, if y is equal to 0, then what should we require? Our hypothesis function, logistic regression hypothesis function, should be 0 or very close to 0. Then we can say our classifier is well, and the corresponding loss is very close to 0 or 0. Now, if it is 0 but our classifier saying now it is 1, then there is a misclassification. The classifier works poorly and the corresponding loss is very high or close to infinity. So these two things we have to impose. Now what we have to understand, that these two functions are to achieve by these two rules. Let one do one by one. Here we plot minus log of h by x. So this is the curve. Now what is this curve? You can see that if y is equal to 1, that what we have to do, we need this h of phi of x should be 1. Now if it is, look, if it is a 1, you can see that it is 1. So if it is a 1 kind of, then the loss is this, cost or loss is this. This is very less. This is very less, is equal to the 0. Because this is the exact, this is y-axis, this is the cost, and it is almost 0. But you can see it is 1, but our function, our hypothesis function of the logistic regression said it is, no, it is close to 0. It is 1, but it is close to, then the loss is becoming very high. This is exactly what we want. So that thing we understand, that this function is going to imposed or going to represent a similar thing, that what we have discussed here for this y is equal to 1. Okay, let's try to understand when y is equal to 0. Now when y is equal to 0, function is minus log of 1 minus h phi x. We plot it, this is minus log of 1 minus h phi x thing. You can see if y is equal to 0, then this and h phi x is equal to 0. So it is, the cost is very less. So is almost 0, close to 0. But if it is going to give 1 when y is equal to 0, its cost is very high, almost going to tending to infinity. So exactly that is what we required. So giving these two equation, actually we can achieve what our classification rules for this logistic regression. Okay. Now this loss function is equal to 1 loss of this function, and y is equal to 0 loss function minus log of 1 minus pi x. These two functions can easily be combined and be written like this, that minus y log of h pi x minus 1 minus y log of 1 minus pi x. Why? Because if y is equal to 1, this term is 0, because 1 minus 1 0, and this term become minus log of h pi x. So ultimately this loss is minus log of h pi x 1 is equal to 1. That is our this thing. Now when y is equal to 0, then this term is going to 0, the whole term, and this term become that the minus log of 1 minus h pi x. So the basic idea is that by using this we can get this equation, and we can write in this combined form. Okay, and another thing, that if we define our loss function in this way, the error surface is more or less, can say, the convex in nature. So what we have seen, that the loss function of logistic regression for the univariate case is j phi 1 by m, sum it up over I to m, m is number of samples, and loss of h phi xi comma yi. So that what we have done before, that was for the single sample. Now we sum it up over all the m samples. And what is our loss function? Is basically y of I log of h phi xi plus 1 minus yi log of 1 minus h phi xi. So what we have to do? We have to find such phi so that we minimize this j phi. And the question is how to find the minimum. So as before, we'll going to the gradient descent for this logistic regression. So this our loss is defined as a j phi, and we have to find this phi such that we have minimized this j phi. Now what we're going to do? We do this particular algorithm that repeat until convergence, so that we can get the global minima. That means, and we have to update simultaneously all phi k's using this formula. Now what is this differential part? It is basically the sum it over I to m, h of phi xi yi, and this is the xqi, and where this gamma is the learning rate. Only difference from the linear regression. So I think this is almost very similar to the linear regression. Only difference is that in this case this h phi thing is basically this sigmoidal nonlinearity over phi transpose x. So what is our h phi x? 1 plus 1 by e to the power minus phi transpose x for this logistic regression. That is the major difference. Okay, as of now we have talked about binary classification. So if we extend this idea for multi-class classification, that means now it is the 3-class problem. It was the binary classification. Now it is a 3-class problem. How we can do this? Okay, and we can extend for more than 3 class also in a similar fashion. Now what we're going to do? Now here we partition this problem in this 3 sub problem. You can see what we are doing. We first saying that okay, now these red dots are the one group and these 2 other groups are another group. So it is 2 groups in that way. So we have to find the decision boundary between these 2 groups. So we can get this YOLO line. So this is that we very much we can do, because by virtue of our previous linear logistic regression what we have discussed. Now the similar kind of thing is, now this is one group and these 2 is a same group. So we can find this kind of blue separator or blue decision boundary by our logistic regression problem. And similarly here this is single group and these 2 are merged, so we can get this purple separator decision boundary. Now here this is basically the same thing. If we can take this into all 3 into accounts, then we can get these 3 decision boundary by virtue of these groupings. Okay, now this is easily can be written in this way, that now this is one group, it's another group, this is the third group. So more than 2 classes, this multi-class classification can easily be done by the 2-class problem, why we have done in the our logistic regression problem, binary logistic regression problem. Now when a novel input, new input come, let's say x is coming, so what is going to do? We have to train the logistic regression to hi phi x in a such a way will predict what is the probability of I or y is equal to I. And for 3 classes we get the 3 probabilities and we go for maximum of this. Which is the maximum? We put okay, this particular new instance is red if it is a highest for red, it going to the green if it is the highest for green, go to the blue highest for blue. In this way we can do this multi classification. This is just a kind of extension of the binary classification what we have discussed. So in this class what we have done, we understood that what is the classification is, then what are the logistic function means and what do we mean by decision boundary for this logistic function. Then we define hypothesis function for this logistic regression, and then how to train a classifier or a logistic regressor, and then how to handle the multiple class. So in the next class what we are going to do, we know that how whatever this linear regression, logistic regression we have discussed, how to optimize this kind of, what are the different issues, mainly we for the overfitting. Okay, for the thank you very much.